How can a galaxy keep building its outer halo when the biggest expected ingredient, black holes, doesn't show up in the way we thought? For years, astronomers pictured galaxy growth as a story with a clear culprit: mergers, energy injection, and the gravitational tug of central black holes. But what if the universe has another dial entirely, one set by dark energy, that slows mergers before black hole-driven feedback can take over? That possibility sounds like science fiction until you realize we already see something odd. Halos around many galaxies look too orderly, too persistent, too star-resistant to be explained by simple merger histories alone. Now add a provocative twist. A new theoretical framework suggests dark energy can predict black hole-less galaxy halos, effectively pushing merger activity into a stall beyond a critical scale we can call beyond C. If this is true, it rewrites what we mean by the growth of structure, moving the steering wheel from the messy center to the smooth background of the cosmos. To understand the before, we need to recall how halos and mergers were traditionally modeled. In the standard picture, galaxies live inside dark matter halos, enormous, invisible scaffolds that pull in gas and stars. When halos collide, their galaxies merge. Angular momentum is scrambled. Gas is funneled inward, and the central supermassive black hole can feed and release energy. That energy can heat gas, regulate star formation, and sometimes blow material outward. Observationally, we see many galaxies with central black holes. But we also see systems where the halo structure doesn't match naive expectations. Growth seems to pause. Satellites stop spiraling in as efficiently, and the outer halo density profiles show signatures of long-lived equilibrium. Meanwhile, dark energy, often treated as a smooth component that mainly drives the accelerated expansion at late times, was usually kept out of the small-scale story. It was background physics, not a merger mechanic. The prevailing assumption was simple. Mergers are governed by gravity and the properties of baryons and black holes. Dark energy is too uniform to matter at halo scales. The open loop is whether that separation is an oversimplification. Here's the core mechanism. Imagine each dark matter halo as a spinning snow globe inside a larger expanding room. The snowflakes, subhalos, move under gravity, sloshing inward during collisions. In purely gravitational dynamics, once a subhalo is captured, dynamical friction and tidal stripping gradually drag it toward the center. That is the route toward a merged galaxy, and often toward feeding the central black hole. But dynamical friction is not a law of nature, it competes with the environment. If the background expansion and the effective pull that anchors structures change, the inspiral clock changes too. Dark energy modifies that clock by altering how the gravitational potential competes with the expansion of space itself. Even though dark energy is smooth, it changes the large-scale boundary conditions for bound motion. Beyond a characteristic scale, the room expands fast enough that the snowflakes lose the chance to drift inward efficiently. The merger becomes a stuttering engine rather than a conveyor belt. Now bring in the black hole-less idea. In many galaxies, the central black hole's feedback would be expected to be a dominant regulator, heat the surrounding gas, prevent runaway cooling, and reshape the inner profile. But if merger-driven fueling is stalled early enough, the central region never experiences the sustained inflow needed for strong black hole activity. In that case, the halo can still assemble in an outer sense. Dark matter builds, gas may settle slowly, and stars can form under gentler conditions. Yet the hallmark black hole-driven transformations become weak or absent. The halo looks like it formed with fewer central events, not because black holes can't exist, but because the timeline and mass assembly path never triggered the expected cycles. Where does beyond C enter? Think of C as a critical threshold in the effective competition between gravitational binding and cosmological expansion, an event horizon of sorts for merger efficiency, not for light. In the framework, as structures grow and their relative velocities and separations evolve, dark energy's influence can tip the balance so that satellites remain in extended orbits rather than spiraling inward. The result is a predictive stall. Merger rates drop, the outer halo maintains a specific density and anisotropy pattern, and the typical sequence merger central fueling strong feedback is interrupted. Importantly, the model treats dark energy not as a passive backdrop, but as a boundary condition that shapes which merger pathways are dynamically viable. To test such an idea, theorists compare predicted halo properties, how quickly mergers proceed, how satellites are distributed, and how long halos remain in quasi-stable states against what surveys infer from gravitational lensing, galaxy kinematics, and simulations of structure formation. The discovery story here is not one telescope capturing one anomaly, it's the convergence of multiple mismatches. Simulations that include standard feedback sometimes fail to reproduce the observed persistence of outer halo structure without invoking specific central energy histories. The dark energy modulated merger stall offers a different flavor. It can reproduce the halo behavior even when central black hole activity is muted by the stalling of infall. In essence, the universe can build halos without turning every merger into a black hole fireworks show. The broader implications are striking. If dark energy can predict merger stalls, then the growth of structure isn't just a gravitational and baryonic story. It becomes a three-part choreography involving dark matter, ordinary matter, and the cosmological term we've long treated as merely late-time acceleration. That means halo statistics, how many galaxies of a given type exist, how clustered they are, and how their outer profiles evolve, carry information about dark energy's dynamical influence on bound motion. It also reshapes how we interpret correlations between central black holes and their host galaxies. Instead of assuming a causal chain that begins with mergers and ends with black hole feedback, we might find that for some systems, the causal chain begins with the background cosmology. Black holes become consequences of merger histories, not guarantees. This could affect estimates of star formation regulation, the frequency of minor versus major mergers, and how quickly galaxies transition between morphological states. In the long term, this offers a new way to test dark energy. If we can identify observational signatures of merger stalling beyond a critical scale, then we can constrain how dark energy couples to structure growth. That includes future surveys that map gravitational lensing over large volumes, trace satellite populations around galaxies, and measure the dynamics of the outskirts where merger efficiency should be most sensitive. The practical world gets an unexpected connection. Improved cosmological parameters sharpen our understanding of the universe's fate, influence simulations that guide interpretation of every other astrophysical measurement, and help ensure we don't mistake astrophysical tuning for fundamental physics. So what have we learned? The old models separated dark energy from halo evolution, treating it as a smooth accelerant that doesn't touch the mechanics of mergers. The new idea collapses that separation. Dark energy can change the competitive balance between gravitational binding and cosmological expansion, creating a critical region where satellite inspiral stalls. When that stall happens early enough, the usual pathway to strong black hole fueling can be suppressed, yielding galaxy halos whose growth bears the imprint of black hole-less merger histories. The halo remains, the central blaze doesn't net. The universe may be teaching us that the biggest ingredient is not always the one at the center. If you want more, subscribe and join us for the next cosmic twist.